Okay, let me start with the slide and then I'll go back with you and fill in the notes that correspond to this. All right, we're now going to introduce something called Coulomb's law and the electric force. So it says, just as there is a gravitational force of attraction between any two masses, Mr. Coulomb found that there's a force of attraction or repulsion between any two charges. And the force of attraction or repulsion is called the electric force. Another name for the electric force is the electrostatic force. Those two words mean exactly the same thing. So we now are learning a new force to add to our force chart. And this force has a capital E as a subscript, and it stands for the electric force. And because it's a force, it's going to be measured in newtons. So let's go back now and look at this. So number 15. So we have the electric force, or the electrostatic force. Electrostatic is the force of attraction or repulsion. The variable is Fe, and the units are newtons. All right, so I want to compare this to Newton's universal law of gravitation, because Newton's universal law of gravitation said that there was a force of attraction between any two masses. So let's pretend that one of the masses was you, and maybe the second mass was, we did in class, the person sitting next to you or across from you. So this was your force of attraction. That was Fg. And we calculated that using this equation, Gmm over d squared. So that G was Newton's gravitational constant. And that number was 6.67 times 10 to the minus 11. The distance had to be in meters, and we would be able to calculate your force of attraction. So person to person, it might have been like something to the negative 7th or 8th power. But maybe the second object was the Earth, and you calculated your force of attraction to the Earth. Now the answer might be like 200 newtons or 800 newtons, okay? But it's going to be a lot bigger. But there's a force of attraction between any two objects, and the point is these two objects are attracted to each other. So it makes them want to move toward each other. And we know that because when I jump up, I end up moving toward the Earth, and the Earth moves toward me because we are attracted to each other. I don't really move toward my friend because our force of attraction is so tiny. I really don't see that, but I guess I really do. All right. The force of attraction between charges, though, is a little bit different because I can have different kinds of charges. So how do you draw a picture of a charge? So they're invisible. They're so tiny, I really can't draw them, but I'm just going to magnify them. And so I'm going to say that this is a 3 Coulomb charge, and then I'm going to circle it. Remember, 3 coulombs is like a lightning bolt. Okay, so this is kind of a bad example. And now I'm going to put another, let's do a 2 Coulomb charge. And they are both positive, so I'm going to put a plus in front of them. So that's how you draw a picture of a charge. Whoops, you know what? We got to make one of them negative. Let's make the 2 negative, so make that a negative. All right, so this has force of attraction between unlike charges, because a positive charge is going to be attracted to a negative charge and vice versa. So I'm going to put an arrow like this because these guys are attracted to each other just like you're attracted to the Earth. So unlike charges, one was positive and one was negative. All right, so this here is Coulomb's law. So Coulomb's law is going to tell me the strength of the force of attraction, just like Newton's universal law of gravitation did. So Coulomb's law is a K, Q, Q, and that could be lowercase q, over d squared. I want you to see how similar this equation looks to this equation. They both start with a constant. In this equation, the K is Coulomb's law constant, and that's equal to 9 times 10 to the 9. So 9 times 10 to the 9. Over here, it was the mass of the first object, the mass of the second object. Now it's the charge of the first and the charge of the second. So if I was number crunching this, I'm going to do that back over here where I have more room. The electric force would be equal to 9 times 10 to the 9, because that's the K value. The magnitude of each of the two charges. We do not include the positive and negative. So I'm just going to put 3. That's the charge of the first one in coulombs. It's got to be in coulombs. The second one's a 2. And then I would need to know how far apart they are in meters. I'm going to pretend they're pretty close. So I'll make this 0.005 meters, and then I'll square it. And we won't number crunch that right now, but that's how I would do that. But when I'm all done, a force is a vector. That means you have to have a magnitude. The magnitude would just be the answer when I number crunch. And I have to have a direction. And so my direction is, because they're unlike charges and they're attracted to each other, I would use the word toward. That's why I should write that in this box here, toward. All right, but I also could have a force of repulsion between like charges. So now I'm going to make this a positive 3. And I'll make this one a positive 2. So when I say like charges, I don't mean that the values are the same. I mean that the signs are the same. So 2 positive charges. They are not attracted to each other. They are repelling each other. So I'm going to draw an arrow like this to show that they're going away. And so when I number crunch this one, I'm going to have to make sure that I use the word away. So the point is, I put the values in the equation, and then my direction is what takes into account the signs. If this was a negative and this was a negative, they would still be repelling, so I would still use the concept of away. All right, the last thing that we have to look at here is sketching a free body diagram. So we probably won't go too much in detail this year on this, but this is something that you should be, I guess, aware of. So this is a picture of, let's call this the electroscope. And these are the strings, and these are the little leaves. But sometimes instead of using leaves, I told you could use balloons. So you could picture this to be a balloon in a balloon. But something else you could do, instead of using those little leaves, you can use little, I'll call them styrofoam balls, but it's not really styrofoam. It's a substance called pith. Pith is kind of like really, really lightweight cork. So it kind of looks like a styrofoam ball, but they act just like those leaves. They can repel and attract really easily. So this is a pith ball. So it says, sketch a free body diagram of each of the forces acting on each of the pith balls in this picture. So this is really like 2 different pictures. In this case, the pith balls are attracted to each other. In this case, they are repelling each other. So if I had to take my pith ball and turn it into a dot, there's a dot. And there's FW that acts on everything. It's hanging from a piece of string, so I'm going to write down FT. But it is attracted to this negative guy. And because it's attracted to the negative guy, I draw an arrow. So that arrow really wouldn't be there in real life. I draw that arrow and I say, oh, that's the electrostatic force. That's why he's attracted to him. And so this is the electrostatic force on this one, and this is the tension. And I can draw an FW here. Same thing over here. I can draw an FW. I can draw the tension in the string. oh, but he is repelled from this positive guy. So the electric force points this way now. So you have to sometimes figure out which way the electric force points by deciding whether they are repelled or attracted to each other. All right, I'm going to stop this one so I can do the examples in the next video.